Hello dear students. In today's lecture, we will continue our discussion of fluid theory of plasma. So far, in our discussions, we have realized that plasma can be treated as a fluid, and we've also seen how the laws of conservation of mass can be applied onto the plasma, which is now being treated as a fluid. Now, the point is, we want to get a framework, we want to derive a framework in which we have equations which can be used to find out the state or position of particle with respect to space and time. So, in this case, we will see how plasma's continuity equation or the equation of continuity can be obtained by treating plasma as a fluid and with a specific approach which is called as the Eulerian treatment, wherein the plasma is confined within a control volume, and this control volume is not going anywhere, rather the plasma is moving or going through the walls of this control volume. So, in our last lecture, we have already seen how to assume this simplified model of a control volume and how we can accommodate, how we can calculate the flux of fluid that is going in and the flux of fluid that is going out. So, we have considered a three-dimensional picture in which plasma is assumed to be moving through the control volume. Right. We will directly start from where we have stopped in the last lecture. So, if it is a three-dimensional picture in which all the three directions x, y, z are intact, so we can say the fluid, the mass of the fluid that is going inside along the one direction, which is the x direction, will be equal to rho u delta y delta z. And this is the volume of the fluid that is going in. We will write its equivalents along the y direction as well as along the z direction. So, along the y direction, it simply becomes rho v delta x delta z, and along the z direction, it becomes rho w delta x delta y. Right. So, rho is the density of the fluid, u, v, and w are the velocities of the fluid along x, y, and z direction. So, delta x delta y, for instance, indicates the area element which is perpendicular to the flow, and if it is in, this is the amount of fluid that is going in. We can also calculate the amount of fluid that is going out in the same direction, can be rho u plus dy dx of rho u delta z. Similarly, rho v plus dou y of rho v delta y delta x delta z, and right. So, now ideally what do we expect? We expect that the total net flux that is going inside should be equal to the net flux that is going outside. So, if the incoming flux is more and if the outgoing flux is less, which means that some amount of fluid mass is being accumulated inside the control volume, right? Or the rate of change of mass inside the control volume dm by dt will become positive. So, inside the mass is increasing with respect to time, which is actually the difference between the rate at which mass is entering the fluid volume and mass is leaving the fluid volume. Exactly opposite, you can have this change or rate of change of mass inside the volume as negative if less amount of mass is going in and more amount of mass is going out. Right. So, in each case, so if there is more amount of mass coming out of the fluid volume than what is going in, you can assume that there is an additional source of source which is actually creating mass from the control volume, and exactly opposite, if there is less amount that is coming out, then you can assume a sink to be present inside, right? But ideally, what do we expect? We expect all of this, the total, the sum of these incoming or fluid that is going in should be equal to the fluid that is going out, or a difference of these two should be 0, or if there has to be a difference, if we have to accommodate the provision of having a source and sink, then the difference of these two should be equal to the rate at which mass is accumulated inside the control volume. So, as simple as that. So, we can write rate of change of mass inside the control volume dm by dt is whatever that is going in minus fluid mass that is going out. So, combining all these things, you can write simple rho u delta y delta z plus rho v delta x delta z plus rho w delta x delta y minus all this rho u plus dou by dou x of rho u delta x times delta y delta z minus rho v plus rate of change of, or the gradient of mass flux minus rho w plus right. So, this is the sum total of mass flux in minus sum total of mass flux that is going out. So, straightforward, we can cancel these three terms, and the first terms within the bracket will disappear, right. So, the rate of change of mass with respect, rate of change of mass or change in the mass inside the control volume with respect to unit time or with respect to time is dm by dt is simply becomes minus dou by dou x of rho u delta x delta y delta z minus dou by dou y of rho v delta x delta y delta z minus dou by dou z of rho w delta x delta y delta z. So, if we divide this with unit volume, this expression, this entire expression with unit volume, so what we get is 1 by delta v dm by dt. Okay, so delta v, we know delta v is equals to delta x, delta y, delta z. Delta v is simply the incremental volume, delta x, delta y, delta z will be equal to, so all of this will get cancelled, minus dou by dou x of rho u minus dou by dou y of rho v minus dou by dou z of rho w. Mass divided by volume will be equal to the density. So, we write dou by dou t as minus times dou by dou x of rho u plus fine. So, this expression that is there on the right hand side, this entire term can be written using a three-dimensional velocity vector, which is defined as u I cap plus v j cap plus w k cap. So, using this three-dimensional velocity, you can write this entire expression on the right hand side as minus del dot rho u. Rho is a scalar, So which simply is just a multiplier. So you can write it as this. So you know that del is I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. Right. So I mean, using, let's say, this and knowing what is del, you get this. It is just a different representation, that's it. Okay, so now you can write okay, so which is the form of continuity equation that we have. So partial change of density with respect to time is equal to the gradient of rho times the three-dimensional velocity. Now, we have already seen the derivation pertaining to the total derivative. How is it different, or what is the need to have a total derivative? Now, we can rearrange these terms, rewrite these terms in a simple way as del dot rho u is equals to rho times del dot u plus u dot del rho. Okay. Now, the meaning of this is that del is acting on this vector. This is this scalar product, and this is the gradient because rho is a scalar. Okay. So, just separating these two terms, we can get a term which is familiar to us as, let's say, minus del dot rho u is equals to minus rho times del dot u minus u dot del rho. Del rho is the gradient of density, which is a vector. So, you have both the terms, both the two terms are actually now the scalars. Okay. Now, substituting this into the form of continuity equation that we have derived just now. Okay. So, what I have done is I have just written the right hand side as two terms, term number 1 and term number 2. I am going back and substituting this information into the continuity equation that I have just derived, which is dou rho by dou t is equals to minus rho times divergence of velocity minus u times u dot gradient of density. Okay, so I can bring this term onto the left hand side, dou rho by dou t plus u dot del rho will become equal to what is remaining on the right hand side, rho times del dot u. Okay, you see this, the term or the sum that is appearing on the left hand side looks very similar to the standard form of the total derivative, which is capital D rho by dt. You have the partial change of density with respect to time plus an advection term, okay, which is equal to the total derivative of the density. So, capital D rho by dt is simply equal to minus rho times del dot u. Okay. Now, this is, what is this equation? This is still the continuity equation. We have just rearranged terms so that we, instead of the partial derivative, we have a total derivative. Instead of a local derivative, we have a total derivative, which also accommodates the advection term, right? So this form of the continuity equation is basically called as the velocity divergence form of the continuity equation. We can go ahead and say 1 by rho capital D rho by dt is equals to the negative of the divergence of velocity. So what does it mean? The fractional rate of change of density while following the motion equal to the negative of the velocity divergence. Okay. So why did I mention while following the motion? Because when you are referring to the total derivative, you are accounting the change in a physical parameter or in a physical quantity while following the motion. Okay, so that is the basic thing. So we have two different forms of continuity equation, although both of them are one and the same. One, d rho by dou rho by dou t is del dot rho u. The second form of continuity equation is this. What is it? The fractional change of density with respect to time is equal to the negative of the divergence of velocity. So density, which density are we talking about here? Density of the fluid, u, the velocity field, okay, t is the time, that's it, okay. So what does it convey? It conveys a simple message that if you apply the law of conservation of mass, you will get an expression which tells you how the mass is changing with respect to time. If it is changing, what are the other parameters which will have this information about this change? Okay, right. Now, like we have seen in the last class, when we are considering plasma as a fluid, we will have two different approaches. One, a Eulerian approach, and another, a Lagrangian approach. Okay. So these two are two different ways in which we can treat the fluid, or we can apply the laws of physics onto the fluid. Okay. So let us consider the second derivation right now, because we've already seen how the Eulerian derivation gives you the form of continuity equation. Now what we will do is we will try to see how the Lagrangian approach is different from this approach, and if we derive an equation of continuity in the Lagrangian approach, will it look similar to this, what we have done so far, or will it be different? Or if it is different, is there any way that we can reduce it, or we can prove both the forms of continuity equations are one and the same? Because the continuity equation simply says about the law of conservation of mass. In whichever way you express it, the meaning of the expression or the meaning of the equation should be the same. It cannot be different. Right. So having said that, let us see with simple mathematics how we can derive the Lagrangian form of the continuity equation. Let us say we write it as the Lagrangian form of continuity equation. Okay. So how is this control volume different from the earlier control volume? The earlier control volume was just a cube or a cuboid which is placed in the fluid, and the entire fluid is moving through this cube. Okay, that means mass is entering into the fluid and mass is leaving out of the fluid, nothing, right? So the fluid volume or the imaginary enclosure that you have taken is not going anywhere. It is just staying there itself, right? But then the second type of continuity, the control volume is called as a Lagrangian control volume, which is just a group of particles. Okay, you identify a group of particles with let's say with a mass delta m. Okay, and you tag it. Okay, it's better to say this way. A tagged group of particles is a control volume. So what happens? So the fluid has an ability or has a fundamental characteristic of moving from one place to another place, right? So as the fluid is moving, the control volume is now this tagged group of particles which are also moving along the direction. So they're going along the fluid. Okay. Now you apply the law of conservation of mass onto this fluid, the fixed mass of particles. Okay. So now let us say delta m is the mass. So we can write delta m will be equal to rho times delta v. Right. Mass divided by volume becomes density. So or we can write it as rho delta x delta y delta z. Okay. So Lagrangian control volume is a tagged group of particles which moves along with the fluid. Okay. So the control volume has a mass of delta m and it moves with the fluid. So delta v is delta x, delta y, delta z. For the conservation of mass, we say that this delta m needs to be a constant for the conservation. Okay. See, for the conservation of the mass, this delta m has to be maintained constant. So if delta m, the rate of change, so if I simply write d by dt of delta m is equals to 0, this becomes the continuity equation, right? But this is the trivial case in which you are necessitating a condition in which mass is maintained a constant. So it's not changing with respect to time, right? But if you have to make a generalized equation in which if at all there is a change of mass, what should it be equal to? Then you have to equate it to something which will bear the load of changing mass with respect to time. As simple as that. Okay, so there is a trivial equation and you have to have a generalized solution in which trivial equation also becomes one of the subset of all the possibilities. Okay, so for the conservation of mass, what do? We try to apply derivative onto this and equate it to 0. Okay, so if it has to be 0, or if the rate of change of delta m needs to be a constant following the motion, right? Now see here, I am specifically mentioning this Lagrangian control volume is a situation in which things are accounted as it goes through the fluid, as the fluid moves from one place to another place. So for the conservation of mass, delta m has to be constant following the motion. So we can write 1 by delta m d by dt of delta m. So I am writing a fractional change of delta m with respect to time, but I am using capital D by dt, which means I am starting my derivation with a total derivative. So this can be written as 1 by rho delta v d by dt of rho delta v, which will be, so I have to expand delta v as delta x, delta y, delta z and apply the derivative one after the other consecutively. So which will be equal to, or 1 by delta v okay. So this becomes 1 by delta x, delta y, delta z d by dt of delta x, delta y, delta z. So d by dt acting on this and this in a chain rule, we can write it as 1 by delta x, delta y, delta z d by dt of delta x while delta y and delta z kept constant, plus delta x, delta z kept constant, delta x, delta y, delta z. Okay, so this is how it looks like. So cancelling out the similar terms, we have 1 by delta x d by dt of delta x plus 1 by delta y d by dt of delta y plus 1 by delta z. Right, simple. Right. Now, since the fluid, the control volume is moving with the velocity of the fluid, right. So, let us say at one instance at a point A, the fluid has a velocity ua, and subsequently at the point B, the fluid has a velocity of, let us say, up. Okay. In that case, the velocity at ua can be written as capital dx by dt, and velocity at b ub is d by dt of x plus dx. So, the difference in these two speeds will simply be equal. The difference in these two speeds will simply be equal to the rate of change of velocity. So, delta u is ub minus ua, which is d by dt of x plus dx minus d by dt of x, or simply put, delta u is equals to d by dt of delta x. So, we have already seen that in this case, in the rate of change of this is the volume d by dt of delta v, the fractional change of volume, right. So, this is going to be du by dt, dv by dt and dz by dt. Substituting this into the earlier equation, we can write as 1 by delta v d by dt of delta v becomes dou u by dou x plus dou v by dou y plus dou w by dou z, which is equals to the divergence of velocity. And the second term that we have is the rate of change of mass, or the fractional change of mass with respect to time, can be written as 1 by rho d rho by dt plus 1 by delta v d by dt of delta v. If it has to be maintained constant, we can simply write it as 0, right. So, mass is, so this is, I hope this is what I am doing, okay. This equation is what I have used. I have applied the total derivative once on the density and again on the incremental volume. So, once I apply for the incremental volume, this is what I get, and the second term is staying as it is. So, now I can substitute what I know for this term, okay. From this I can write 1 by rho capital D rho by dt plus del dot u is equals to 0, or capital D rho by dt is equals to minus rho times del dot u. Fine. So, this is the form of the continuity equation in the Lagrangian framework. Okay. So, let us try to wrap up what we have done so far. So, earlier we have started with the Euler control volume, and we have obtained a simple divergence form of the continuity equation, where the partial rate of change of density is equal to the divergence of density times velocity. Using vector identity, we separated this, we rewrote the right hand side into two terms, and then we realized by doing some algebraic rearrangement, we realized it can be written in terms of a total derivative, and the fractional change of density with respect to time is equal to the negative of the velocity divergence. So, this is the form, right. So, this is one more variant of the Euler's control volume driven equation of continuity. But then we took the Lagrangian control volume, and then also we realized the form of the continuity equation is one and the same. Okay.